um, as it is. Sorry for that. And hopefully next week it will be fixed. I would definitely report this. So Gaussian process regression, as I said, a very different method. Also not easy to talk about, and potential for a lot of errors on the slide that might be much harder to see for you now. But if you find errors at home, do let me know. Chocolate awards are still counting. But before we start, oh, this is also not working. It's really big fun. Here we go. Before we start, you should have assignment 9 online now, which is the hackathon, second hackathon. You should be able to find the material under week 12. I apologize for having to talk on the small screen today. And it's all about climate modeling. So I promised this a long time ago that you look into something called climate model emulation. So specifically, you look at output from a state-of-the-art climate model that participated in the so-called coupled model intercomparison project 6. I will talk about this intercomparison project in somewhat more detail next week. But here we focus on one specific grid location because this output is really quite high dimensional. So not laptop adjusted. So we will focus one particular grid point, which includes Karlsruhe. I thought this makes it somewhat more exciting. And what typically happens is, so when you run these climate model simulations, you have an Earth system model, right? Which here by this icon Earth, is represented in a far more simplistic fashion than it really is. It's some of the longest, most comprehensive computer models you can find based on differential equations, based on parameterizations of processes, right? So everything that you think is of relevance to the time scales that you try to project. So more complex also than a weather forecast model, which often doesn't run a deep ocean or upper atmosphere or cryospheric long-term processes or carbon cycle components and so on. What you're essentially trying to do is implement this system in many different ways because there's no perfect way to model the world. So you have a lot of different of these Earth system models. You focus on one specific one here. And then you try to run different scenarios, right? And like years ago, a colleague physicist told me, yeah, but how do you actually know what is going to happen in the future in terms of scenarios, right? That's already a terrible mess. And this is exactly it, right? So you don't know what we will do in the future. So you run typically a number of different scenarios, right? So best case scenario, we will just have some magic wand and immediately start mitigating emissions, or have a strong policy enforcement that CO2 emissions are not ramping up, that we are cleaning up everything at once, to let's just go on business as usual. So maybe you can even make this out in the back, this is the red line here. Business as usual, everyone just tries to industrialize and build their economy based on a fossil fuel driven economy as fast as possible, so worst case scenario. And then a few scenarios in between, right? Compromises, different scenarios you could imagine for different parts of the world evolving differently, for example. And this can give rise to very different trajectories in certain key climate forcing agents, as we call them. So that's a term I will use as well in the assignment 9. Climate forcing agents for me are external aspects we impose by, for example, emitting human anthropogenic emissions of not just greenhouse gases such as carbon dioxide and methane, but also aerosols. So aerosols you've seen a few talks about, affect clouds, but also have a reflective effect in many ways. There are some aerosols called black carbon aerosols, which can also be absorbing because they're black, right? So, but for example, SO2, sulfur dioxide, is a precursor of sulfate aerosols, which are actually quite significantly cooling climate as far as we know, historically speaking as well. So if we clean up our air, that might be sort of a climate penalty on top of it, because we might have hidden some of the warming underneath aerosol cooling in the past. So all these different input features can vary in different ways under these scenarios, and they will give rise to different outputs, right? So the Earth system model has its intrinsic weather, internal variability, and long-term timescales of climate change, because as you put these things into the atmosphere, you change the Earth's energy budget. So you have a slow response of the system equilibrating to that forcing, right? And as you change that forcing, it's sort of constantly readjusting. And outputs essentially include physical variables across the entire atmosphere, the oceans, the cryosphere, and so on. But what policymakers or analysts typically look at is outputs like precipitation or temperature. So how are these distributions shifting? Are they getting wider, right? The extremes may be getting wider and so on. And that's especially not just globally, but also regionally. For variables like precipitation, hugely important, right? Because in some regions they might get drier, other regions might get wetter, or in some regions nothing might happen at all. And it's especially precipitation is quite a noisy variable. But now, okay, so I'm already running out of time. We'll just press buttons here underneath my desk from time to time to see if there might be some sort of ridiculous resolution of this situation. But what these climate models are very expensive. So this is sort of indicated by this icon up here. So we run these on supercomputers. So we are usually limited for each model to run a very limited number of these scenarios, right? Which means if you wanted to explore different aspects, say, oh, let's try to reduce methane emissions much more quickly because methane has a shorter lifetime, as I've told you a few weeks ago. So maybe that might be a quick resolution to stay below 2 degrees without having to tackle CO2 emissions as much immediately. 2 degrees global warming, that is. So basically policy informing scientists, especially social scientists, try to basically get more scenarios of this kind, and this is extremely computationally expensive. So the idea is, could we not build a machine learning emulator, as we call this, so a substitute surrogate model that learns from the data that has already been produced by these Earth system models, right? And instead does the mapping between the inputs and the outputs. Right, so you have the big data. I told you this is in total several tens of petabytes. We are flying around somewhere ready for download. So why do we not just use that to build cheaper emulators you can run once trained very quickly for a range of different scenarios? And this is what you're trying to do for one particular grid point in Europe, using these climate forcing agents for scenarios that have already been run, and also sea level pressure fields, because for precipitation, the weather situation is very important, right? So it's not just the long-term varying input signal, but also the high internal variability that drives, let's say, a low pressure system being connected to extreme precipitation. So you try to predict regional precipitation rates. So I hope the worksheet should be quite self-speaking. Otherwise, do post on the discussion board, as you sometimes do already. Yeah, at least I understand this board now much better. So I know it's also showing nothing here for window projection. So I guess that's at least consistent. Okay, so last week, very quickly, we talked about causality, because in machine learning, we usually look at learning from correlations, right, that are predictive, also on test data, but it's not a causal relationship. So if something changes about the system, these correlations are auto break. And we talked about how we could formalize this following structural causal models. I also mentioned there are various ways of trying to formalize this, but we looked at these graphical models and, for example, looked at something called the do operator to block out certain paths in this framework and establish causal effects. And then we also briefly touched on how quantifying causal effects is somewhat difficult as long as you can't do the do operation in reality, right? So you have to indirectly estimate this from data. And for certain simple examples, that's analytically tractable. For more complex examples, it becomes more complex. And then we also talked about how you could discover the causal graph in the first place. So this is causal discovery. And for certain simple systems, again, that's quite intuitive, that certain causal structures based on the relationships you find in data are the only few options. And then finally, this goes into assignment 7, which I believe you might be working on now. Looking at the time series graph, so here you also have to take lagged relationships into account. It makes things easier because causation can't go back in time, at least we don't believe that, and high dimensionality is the thing you pay for it because you have to take lagged relationships into account, and so on. But this is something you look into during the assignment. So okay, so for today we're now slightly time constrained, even more than I was before. So some of the slides will fly by quite quickly, but that's not entirely disadvantageous, because otherwise I think some of the slides are it's something you can read at home, and it would be better if you read it at home instead of me going through every single analytic step. So it's good to have the material, I suppose, but maybe not particularly beneficial if on a small screen I go through this rather quickly. But what I want to bring across today is sort of the basic idea behind Gaussian processes and how they are used for regression, why it's a so-called non-parametric method, and some advantages and challenges in the practical terms. And you will see this in assignment 9, where you can use it, and you have quite a large sample size, and then it becomes a RAM issue basically immediately, right? So then you have to use sparse methods to even be able to run it at all, probably on your laptop. We also look into things like how can we tune. So even though it's a non-parametric method, you might well be aware that this just means there's still hyperparameters that we can tune, what happens in extrapolation, and so on. In terms of sources, Gaussian processes have been around for a while. So the Bible, I would say, is the Rasmussen and Williams book from 2006. It's easily available online. Especially I draw today on chapter 2, but also some of the other chapters I mentioned here, more or less in depth. I follow some of the roadmap they suggest as well for introducing the concepts. But if you like to see an alternative viewpoint, Murphy and Bishop are also slightly less comprehensive, but still good introductions to kernel methods and Gaussian processes. And once you have established those basics, and maybe you've already seen them in other lectures, I would recommend becoming a little bit practical. And if you want to have practical worksheets, Jupyter notebooks to go through to cover some of the theory concepts as well, there's a summer school in Sheffield, which typically happens annually. I've sent there a student in the past, which is quite good, but I guess it's not a pure introduction. I assume some background knowledge about those methods. So, but you can find free materials online, pretty much updated every year. So, for example, if you try to do this for the assignment 9, this might be a good way to get into GPy, one of the software packages. Okay, so GPR in a nutshell, we are talking about probabilistic methods, which simply expressed means that we don't just have predictions like for the frequentist methods, and there maybe we have to do some bootstrapping or parameter replacement to get some uncertainty intervals. This method comes with empirical confidence intervals on its predictions. And that's one of the main reasons why people in practice use it, to be honest. So that's often a justification if they say, oh, we use GPR in this paper because we want to have an intrinsic uncertainty quantification. There are certain pitfalls to that because it involves, I on purpose expressed it here as empirical confidence intervals because it depends partly on your decisions. So an uncertainty that depends on your decision is not, you shouldn't, there might be more extreme events out there, that's the bottom line. So how much you can trust it is sort of a little bit in the open, but it comes as part of the method, which is helpful in many ways. And very important for GPR, for Gaussian process regression or Gaussian processes, will be the covariance. So we will talk a few kernel designs which make it highly flexible and non-linear. We will also talk about why it's a non-parametric method, or I can basically summarize it here now. So non-parametric in the sense that we don't have a set of parameters like in a frequentist neural network or in a linear regression where we have a specific set of slopes we want to learn, parameters we want to learn, and this sort of brings in the complexity of the model. Here we potentially keep track of all the samples that we have seen at training, which makes it so-called non-parametric. It still means that the kernels that you learn and fit have parameters. So these we can later on optimize. And because, I mean, as soon as we talk probabilistic, Bayesian isn't far away. So Bayesian methods work with a prior distribution. In this case, this would be the kernel, because we have to specify some assumptions about the set of possible functions. This will make much more sense later on. We want to fit about to use the data to update that prior to get a posterior distribution of functions. And this is where Gaussian processes come into play. So basically, that's Gaussian processes assume normality, normal distributions of random variables. So normal distributions you have seen many times before, I assume that they have some nice properties, right? So integration is easy, combination, multiplication, summation becomes somewhat easier. So Gaussian distributions have some very nice properties that we can use here. But ultimately, they are also a good equation to describe stochastic processes, which this fundamentally is. A Gaussian process is a stochastic process describing the stochastic behavior of properties of functions that we want to constrain to predict. And what I often feel lacks, but also makes it slightly less technical in a sense, in an introduction to Gaussian processes, is some sort of intuition. So when we talk about about random variables, right, we have the normal distribution. I don't think I have to recap too much about the normal distribution, but I have this capital letter X here, which stands, in this case, still on later slides I will use it for data, but in this case it stands for random variable X, and it's random because it has some uncertainty to it, right? So given an input lowercase x, you could, draw a normal distribution with a certain width, right? So it's non-deterministic. And what we try to do in probabilistic or Gaussian process regression is basically we have points in the input space, okay, which are not deterministic. So you could have different points for a given input value x, and you get an output prediction f of x, which is, as I said, not deterministic. So you have sort of uncertainty on the value you try to predict. So you could, for simplistic reason, plot this as two uncertain distributions with some sort of average value that is most likely for this particular point, and then a spread around that to values that become less and less likely. Now, this is all taken from a not perfectly written tutorial by Wang, but I think it helps to get the intuition across. So if you had, say, 10 samples from these distributions at values x equals 0 and x equals 1, then you could ask yourself, and this is basically what we do in machine learning all the time, what would be a good prediction based on the points we have here for, let's say, x equals 0.35 or some value in between, right? And a simple way would be to draw linear lines here, right? Connect the points of the two distributions. Again, you could do this in a variety of ways, and then take the average value of those functions, that's x equals 0.35, right, as a possible value, and the standard deviation across those values as an uncertainty estimate for that value. So fundamentally, it's down to how do we connect these two distributions, and you could think about sampling the space more densely, right? And again, drawing linear lines, and you would see that it becomes somewhat more noisy, but you also have a question of how many points would you like to sample to characterize that well, basically. But the key point is here, how do we connect, how do we interpolate between the points that we know about? And you can already see from this distribution up here that this becomes firstly very noisy and secondly very locally defined, because say you would have this observed point here, or this point here, then you can see that it only depends on the value of the previous point and this point. So you can have very sharp transitions between samples, right? And this is something that we are not particularly happy about, because we talked about overfitting and how we often try to build functions that have a certain level of intrinsic smoothness because we believe the system has a certain level of intrinsic smoothness to it. So inputs, like if you would be at x equals, what is this, 0.88 or 0.92, you would hope that the values are somewhat constrained to be somewhat similar, because they're close in input space, they should be close in output space. So how can we do this? It's basically a smoothness criterion, which also protects us from overfitting data. And the basic idea we will pursue here is to say, let's treat these distributions here as Gaussian distributed random variables. Let's try, because Gaussian distributions have the property that they can be combined quite nicely, let's look at the covariance of these Gaussian distributions to create a joint Gaussian distribution, which helps us define how we would draw the line between these points that we have observed, as a very basic intuition. And by doing this, and this will be defined through the covariance between these random variables, we can define different properties, how we would like to connect those points, okay? So that's a very basic intuition, and it's fundamentally the same what we try to do in all machine learning. We try to connect those points in a reasonable way using some smoothness criteria, and usually overfitting would be too noisy, right, to connect those dots. But here we have a probabilistic random variable, so we try to do this because we also have this uncertainty on the values themselves. They are random variables, right? And this way we sort of keep the probabilistic idea from the outset in our approach. Does it make sense as an intuition? So I will have to run through this more quickly than I planned to. But very important for this is clearly the idea of Gaussian distributions in the first place and how we can combine them. So I would go back to a few of these issues from time to time. If you feel revising this material that you have to brush up on some of these concepts, the earlier sections of the books I cited as literature recommendations are really good to do that. It's basically treated either in one, like in chapter 1 or in the appendix. So usually these contents are so Gaussian randomly distributed variables, the joint distributions, the conditional distributions. You will find a lot about this in the appendix of Rasmussen and Williams and in the earlier chapters of Murphy and Bishop. But I point you to those, and I've already pointed you to them on the literature recommendations. And then we go through the definition of Gaussian processes again, and the kernel trick, so to speak. Then we look at how we can use this. These are basically formula, right? So once you know how Gaussian distributions behave, especially joint or conditional Gaussian distributions, you can derive some simple formulas that allow to quite effectively compute predictions using Gaussian processes. And then we can add some noise to them. So what happens if we are not too sure about the training data? And then I will go through how do we actually learn the hyperparameters for the so-called kernels, select models, and how can we, and that's practically probably the most relevant section, even though it's mostly a collection of slides for you to run through when you try to design your kernels. And again, there are a couple of examples in assignment 9 that I provide, very introductory examples though, that can be well optimized. But how can we combine different kernel functions to an overall kernel design? And this you can do with a variety of software packages. Nope. Okay, so multivariate normal distributions. You might have seen the formula before. It's basically a probability distribution, and we can exploit this in a multidimensional space. So instead of just one dimension, we might have 2 dimensions or more. And we have a covariance across the dimensions, in total d, let's say d dimensions, so this can be very high dimensional. And they will have some covariance, right? They have their internal variance, sort of a marginal distribution, right? And then they have a covariance which describes the relationship across dimensions. And the relationship across dimensions is clearly what we partly want to pick up on using these sorts of methods, right? Because that's where our predictive skill comes from. As a shorthand notation, we often just use this normal distribution n and in brackets the average value, or the average, like the mean vector, right, of dimension d again, and the covariance matrix of dimensions d times d. And for the Gaussian distribution, the covariance, you could have other distributions just equal to this variance matrix. And again, I point to Bishop for some of the derivations here. And if you want to look into multivariate normal distributions, there's a super long blog by Bagheri, which are linked here. So just in case you need to brush up on some of these concepts. So covariance is where the relationship between variables with a probabilistic interpretation comes from. And I'm sure you have seen this before, but I will write the covariance matrix sometimes as sort of, we have the diagonal term, right, of the covariances between the variable with itself, which is basically the variance, right, and then you have the covariance on the diagonal terms, which describe the relationships across random variables. So this might be different predictors, for example, in our input space. Okay, so let's get to the actual topic, which is Gaussian processes. So the tight definition provided by Rasmussen and Williams is: a Gaussian process is a collection of random variables. I wrote for myself here multivariate Gaussians, any finite number of which have a joint Gaussian distribution. This is just a statement about Gaussian distributions. The joint distributions of Gaussians are also Gaussian, basically. And this gives us some nice properties to optimize over, and later on so do the hyperparameter optimization, for example. Now in Gaussian process regression, you could also do classification with a few more tricks, but I will not talk about it because we're already limited in time, and I hardly ever use it for classification. Maybe I should. Yeah, in principle, it's an unsupervised, a supervised learning method, right? So But now in Gaussian process regression, each random variable in this collection of random variables is a function. So the GP describes a distribution over functions, which you then try to constrain, so possible functions that you then try to constrain based on the data evidence. And each of these Gaussian processes is fully defined because it's assumed to be a multivariate Gaussian by its mean and by its covariance, right? So this fully defines the function. Again, an advantage of using Gaussian distributed random variables. And you will often see the notation that these functions, the Gaussian process, is simply denoted as GP of the mean function and the covariance function. The covariance is defined between any two input points, right? So this is often the notation x or x and x prime. This just describes the covariance between two different input locations, however they might be defined. And usually it should be smaller, as you will see for certain kernels, if the inputs are far away from, very distant to each other in the input space. And then for notation purposes, I will set the mean here to 0. This is quite commonly done, and you can do this quite easily as well in practical purposes by normalizing your data, right? But it simplifies the notation in the following. It will sometimes point out when it becomes important. Okay, so we have the Gaussian process. We set the mean to 0. The input variables could here be different points in time. They could be whatever you have as predictors, right? But okay, the random variables are actually the value of the function at these input locations. Very important, right? It's the distribution over the functions. Now you could have in principle infinitely many inputs, x, so infinitely many such functions, but clearly in reality, and this is also what I will use in the notation here, following Rasmussen and Williams, you would usually have a set of training data points defining your e's, so index I for an actual data point for the input xi and the output yi. It's just a practical purpose. I might be able to jump this, but just as a brief introduction, given that we talk about Bayesian methods. So often people use Bayesian linear regression to motivate Gaussian process regression because it puts you again into the situation where usually in linear regression you would have this parameter w that you try to find a single value for using a linear regression. In a Bayesian approach, you instead define a prior distribution of likely parameters over the coefficients you would want to fit, and then you use data evidence to update this prior to a posterior distribution of that kind. So this goes back to Bayes' theorem, and this is how you ultimately try to also later on calculate, using normal distributions, the posterior mean estimate for your prediction and the uncertainty around that. I will provide a few formula for this. The way you can use Bayesian linear regression is then also to motivate the use of kernels for the covariance function. So you've seen pretty much lecture 2 or so that was when we talked about multiple linear regression, right? So you have more dimensions, multiple parameters w. In this sense, you could again see this as a prior over the weights with a certain covariance, and let's say the mean value to 0. And you could have this basis of feature mapping function theta, or phi, sorry, in this case, of x, which could give you some sort of nonlinear transformation. This might be in polynomial, this might be a highly nonlinear function of any kind. And this would be for a specific input sample. So if you generalize this over all training samples, you would just have capital phi, a matrix of capital phi that transformed the input data to a new space. It's basically a transformation of the data to a new space, which allows you to incorporate nonlinear transformations, right, in this framework. So if you wanted to write the mean and the covariance for this, you would just get this, and the mean is pretty boring in this case because we set it to 0, but the covariance is pretty exciting because what you can see as an expression that you get is just the transformed input data times the covariance matrix P times the, let's say, another input point, the function at a different point, because it's a covariance between different input points, again transformed through this nonlinear functions. And that's an expression you might have seen before in kernel methods. But what this effectively does for us is that because we assumed a Gaussian distribution, we get this covariance expressed in this term, which we can generalize to any function values f of x, right? So any sample would have the same properties of being jointly Gaussian here, and creating basically a Gaussian process of different functions for different inputs sharing a certain covariance function. And then comes into play a sort of a light motivation of the kernel trick. So because we know about certain properties of the covariance metric, being positive definite, we can rewrite the covariance matrix as a sort of a square root of the covariance matrix square, and we can redefine a new basis function of the covariance matrix to a square root of times the original data transformation. And this is often how kernels are being written, as a simplified psi x times psi x prime. It's just a different way of writing it. But what it ultimately allows you to do, in a nutshell, is to apply nonlinear transformations to your data and transforming a potentially linear problem into a nonlinear problem using quite simple transformations that are easy to compute. Maybe just as a notation for later on, so we have this lowercase k and an uppercase k. So the uppercase k is just if we calculated the covariance not just on one pair of input samples, but let's say over the entire training data set, or so the data that we fitted it to. Then we would also have this capital phi here of x. Okay, so this is just a different way of representing the transformed covariance using base functions that essentially give you potentially nonlinearly transformed ways of your data. Okay, who would like a break? Or shall I just push through? Okay. I will push through and try to get through this fairly quickly, but I would recommend, given the size of the screen today, that you have a look at these slides yourself again, and if you spot any errors, just let me know. Any mistakes, I mean. Nothing to shoot at. Okay, so the specification of the covariance function, because it has had this implication for the values we get out for each input point gives a Gaussian distribution, a joint distribution, multivariate distribution over functions. And to see that, because it's not so intuitive if you see it for the first time, would be once you have defined this covariance to draw samples from it, right? To create those functions, similar to what we've seen in the introductory slides. And there's a recipe, again, I took this from Rasmussen and Williams, which basically runs through the context that you first have to define your input points at which you want to evaluate the covariance matrix, and you can write this out. And then you can use basically this distribution that you created of covariances to draw samples from at random, to create, for the inputs, a Gaussian vector f star, as it's denoted here, for inputs x star, that represent values randomly drawn from that distribution. And then you can plot those generated values as a function of these inputs x. And if you do this in 2 dimensions, which makes it easier, using a kernel which is quite common, which is the radial basis function kernel, also called the squared exponential, which is pretty much just measuring the distance between your input points, squared, normalized by some length scale parameter L, and the exponential function. So if your inputs are very close to each other, this should be close to 1, this term, right, because it becomes 0 in the exponent. And if they are very distant, because you have a negative sign, you take the absolute value, the covariance will decrease, right? So this just describes what you might want to have in your data set, that input points that are close in space give you a larger output value f of x, okay? And if you sampled from those distributions, you would get something like this, which you already saw on one of the intro slides at the beginning. But this is just 3 samples of that distribution. You could draw many more, right, evaluate across different inputs. And you see that you get different possible functions generated by this Gaussian process. Now the key question, what we usually have, is what you see on the right side. So this is your prior, right? So you have your Gaussian process of defined functions. This is your prior. So once you get actual data to constrain your Gaussian process, how would it be updated so that you get uncertainty estimates on points that you haven't observed, right? And should you also have an uncertainty on the points that you have observed, right? So this would be adding noise. And what do you do in between points and beyond those, right? So how do we get to this posterior? And for this, let's first focus on assuming that all these observations we have are noise-free so that we can fit them quite so neatly as they are indicated here. And I could make a really long story out of this, but again, I can refer you to Bishop that runs through this. It's in chapter 2, the basics on multivariate Gaussians. But the idea is that if you have multivariate Gaussians, right, so random variables distributed as a Gaussian distribution, so in our case this would be the functions specified by the Gaussian process, then you can create disjoint subsets of these random variables, like this, for which you can define covariance matrix entries associated with each of these data sets, right? And if you transform this sufficiently, what actually you want to do at prediction stage is so at prediction stage later on, you will have a new set, let's say xb, in this case it would be f star or so that you try to predict, so this would be your test data, and xa would be your training data, okay? So you want to make a prediction, xp, for a Gaussian process prediction on test data based on what you already know about xa. So it will turn around in terms of the conditioning here on the next few slides. Unfortunately, I couldn't update this, but this is why you are here, right? So if it doesn't make sense at home, you know I said actually the index will be reversed. But what you will try to do is to predict xb conditional on a. So all the indices here of a and b will swap. But using these relationships, which can be quite easily derived for conditional Gaussian distributions, you can quite easily derive an expression for the prediction of the mean value for your test data, conditional on the training data, and for your covariance on your predictions, conditional on your training data. I hope you can follow me here. Some of you not, others will say, I will look at this at home. But to a certain degree here, you have to believe me, this formula, or I could spend 15 minutes going through what Bishop wrote on 2 pages. I don't see the point in this, especially today, given the time pressure we have. Okay, so we assume the data is noise-free. So using the formula from above, we could say we want to update our prior, right? Update, very important, I could have highlighted this, with training information to form the posterior, right? So in this case, similar to what we had on the previous slide, we could look at f being our Gaussian process for the training data and f star the Gaussian process for test data. And this will have a covariance between, basically you have to estimate the covariance on the training data, the covariance between the training and the test data, right? And create a complete covariance matrix, and then using, so this will be n times n star matrices, so this becomes very high dimensional very quickly if you have a lot of samples. So this is why you will run probably into RAM issues if you apply this in assignment 9 for the hackathon. Okay, so we have this expression, and we basically want to know f star, right? So how f star is being distributed both in terms of the mean value, which might not be 0 anymore for your test data, right? So this is just something we assumed here notation-wise, but your prediction on the test data might well not be 0. And you want to estimate the covariance for the test data, so your uncertainty on your predictions. And using the formula I wrote above and swapping the indices, because now B, you want to calculate B, which is f star conditional on A, the training data, you should get an expression like this. And it's very convenient now that I cancelled out some of the terms. So because here, because we assumed the average to be 0 to begin with, you lose the terms of the mu terms here, because otherwise this would get somewhat more cluttered. But basically you calculate your Gaussian process predictions f star conditional on given your training data, your test data x star, and your training data x, and your prior f Gaussian process. And then you will get an expression like this. You can do this at home for your average prediction. and after the comma for your covariance, the revised covariance. And you can do this by using this formula combined with the covariance matrix as I've written it up here. And I had to go back to the slide a few times to update stars, upper stars and lower stars and blah, blah, blah. But I'm pretty sure it's error-free now. Okay, and then basically, once you have your posterior distribution, you can sample any predictions you like from that distribution for predictions, including the mean and the covariance. Originally I had a question here, but shall we drop this, given the time? Say, well, let's just do it. Some